Actually, in the previous part, we described the recurrent neural network architecture. We discussed how to calculate the different parameters like net parameters and out parameters for nodes of different layers. We also discussed how to calculate the error. Now we use these calculation scores and backpropagation through time to update the weight of these neurons. Actually, backpropagation is a partial derivative with respect to some given weight. For example, we can take the backpropagation with respect to V2, with respect to W12, with respect to W01, with respect to V1, V0, and so on. Actually, backpropagation calculates the amount of changes in the weight of neuron which affects the error, and we use this amount which affects the error in calculating or updating the weights of the neuron. But here, as we discussed earlier, recurrent neural network architecture is slightly different from traditional deep neural network architecture. Here we take the inputs at different time intervals. So instead of applying a traditional backpropagation algorithm, we apply the backpropagation through time algorithm. So we start our backpropagation algorithm from our last input. So we have the last input at t is equal to 2. So we unfold the network over t is equal to 2. So this unfolding will remove this portion and we consider this as a final output, and after that we apply the general backpropagation algorithm applied by deep neural network architecture, and by using this architecture we can update the weights. So here the backpropagation will follow this path. We will use this path and update these weights. So to calculate the partial derivative with respect to V2 of E2 with respect to V2, we take the differentiation of E2 with respect to V2. Now here all the differentiation will follow a chain rule. This chain rule is just the opposite of the information flow path. For example, in this case you have seen that the information flows like net part to out part, out as 0. Similarly, at this part the information flows like net part, out part, and here also information flow is like net part and then out part. Here also net and out part. So in the traditional forward pass, the information flow in this direction. In the back propagation, the information will flow in this direction. So to apply the chain rule for this E2 with respect to V2, apply the chain rule in the calculation of partial derivation of E2 with respect to V2. We will use this information, means E2 to out O2, out O2 to NO2, net O2 and net O2 to V2. So our derivation path will follow the chain rule. Derivation of E2 with respect to out O2 and out O2 with respect to net O2 and net O2 with respect to dV2. So in the next part we will calculate these separately and take the multiplication to calculate this gradient with respect to V2. So here, calculating the differentiation or partial derivation of E2 with respect to out O2, we will take the expansion of E2 that we derived in previous session, that our E2 is a half of given O2 minus out O2 whole square. So we'll just copy this and use it here and take the differentiation with respect to out O2, and this will be the result. After calculation, this will be the final output value. The next part is out O2 with respect to net O2. So we can calculate it. So our out O2 is just a sigmoid of net O2, and in the previous session we discussed that important feature of derivation of sigmoid functions. If we take the differentiation of sigmoid function Sx with respect to x, then it gives such kind of relations, means Sx into 1 minus Sx. So this is the same kind here, same type of relations exist here. So in this case our derivation will be out O2 into 1 minus out O2. So by putting the value of out O2 and we can get the result. Just make a slight correction, that after passing the value of out O2 0.5777 and it will be equal to 0.2439. So we can just correct this value. Similarly, we can calculate the next part, this part, and this is very simple. Just we take the expansion of net O2 that we derived earlier. So our expansion of net O2 is V2 into out S2. So we'll just copy this here and take the differentiation with respect to V2, which will be the out S2, and this is the value. So we'll take all three values together and take the multiplication, and this is the gradient with respect to V2. Now, as we discussed earlier, we can take the gradient with respect to V2, with respect to W12 and with respect to W01, because after unfolding at t is equal to 2, the back propagation path will covers all these weights. So now calculate the gradient with respect to W12. So here again we will just derive a simple relation again, net out, again there will be out and net. So here E2, the back path will be from E2 to out O2, out O2 to net O2, net O2 to out S2, out S2 to net S2, and then from net S2 to W12. So the same chain will follow here in the chain rule of derivation, in chain rule of differentiation. So we can expand partial derivation of E2 with respect to W12 as differentiation of E2 with respect to out O2, E2 with respect to out O2, and then out O2 with respect to net O2, and then net O2 with respect to out S2, and then out S2 to net S2, and then net S2 to W11. Now we will take these derivations separately and take the multiplication of all derivation results, and which will be the gradient with respect to W12 or partial derivation of E2 with respect to W12. We will use this partial derivation of W12 in updating the weight of W12 in the next step. So DE2 out O2 that we already calculated here. Okay, updating this weight and replacing it here, we will make a slight difference in calculation, so not 0653. So we will use this result instead of this. Now come to here. So again this part is already calculated. For this part, out O2, partial derivation of out O2 with respect to net O2. Out O2 shows some sigmoid relations with net S2. We can see here in the, so this is the out O2 and net O2 based relations. This is a sigmoid relations. We already defined the nature of sigmoid derivations. Here in this case we already defined the nature of sigmoid derivations. So in this case it will be equal to out O2 into 1 minus out O2. Just by putting the values we can get this result. Similarly, to calculate this part of the derivations, we will use the expansion used to calculate the net O2. So here in the previous step we calculated net O2, which is equal to V2 into out S2. So we will take this copy, we copy it and take the differentiation with respect to out S2, and which is equal to V2, which is given value, and it is 0.5. Similarly, out S2 with respect to net S2, again same sigmoid type of relations between them. You can see here out S2 and net S2 based relations is sigmoid relations here. So the differentiation will follow the same rule again. So it will be out S2 into 1 minus out S2, and this is the differentiation result. Now the last part is calculating the differentiation of net S2 with respect to W12. So we will use the expansion of net S2 that is given here. So our expansion of net S2 or derivation of net S2 that we calculated in previous lecture is this. We just copy this value, copy this expression, and put it here and take the differentiation with respect to W12, which will be equal to out S1, and this is the value. So finally we can get the partial derivative of E2 with respect to W12. By putting all these values we can get 0.0077. Here we will make this okay. So now the second part is, as we discussed earlier, the back propagation path for error at E2 will follow this path. So the next weight which comes in this path is W01. So we will take the partial derivative of E2 with respect to W01. So it will again follow the same type of back propagation path and same type of returning relations from out to net, this out O2, net O2, and again it will follow the rule like this is out part, this is net part. This will again follow the same rule. this is out part, this is net part of S1. So here our back propagation will follow the path from E2 to out O2, out O2 to net O2, net O2 to out S2, out S2 to net S2, net S2 to out S1, and out S1 to net S1, and net S1 to W01. So this is the returning path. So this is the chain that derived from this returning path. So this is partial derivation of E2 with respect to W01 is partial derivation of E2 with respect to out O2, partial derivation of out O2 with respect to net O2, and partial derivation of net O2 with respect to out S2, and again partial derivation of out S2 with respect to net S2, and again partial derivation of net S2 with respect to out S1, and from out S1 to net S1, and from net S1 to W01. So in the previous step we have derived some relations till here. So we will not repeat these calculations. We will just calculate three derivations: the net S derivation of net S2 with respect to out S1. So for this we will just expand the net S2 derivation. So our net S2 is calculated like U2 x2 plus W12 out S1. We'll copy this. Copy this here and take the differentiation with respect to out S1. It will be W12, whose value is already given. You already have this value 0.5. Now the next part is out S1, differentiating out S1 with respect to net S1. You can see here that out S1 and net S1 is related to each other by through a sigmoid function. So differentiation of sigmoid function will result in such type of relations, and by putting the out S1 value here we can get this score. Similarly the last part is net S1, differentiating net S1 with respect to W01. So here we will use the expansion of net S1. So our net S1 that derived earlier is U1 x1 plus W01 out S0. We will copy this value here. So after taking the differentiation we will have out S0. Now we have these three values calculated. These are already calculated, so we will put all these values here, and after multiplying we will get the partial derivation of E2 with respect to W01, which is equal to 0.0007. So at time step unfolding time t is equal to 2, we calculated the partial derivation of E2 with respect to V2, with respect to W12, and with respect to W01. Now with respect to time we apply the back propagation again at time t is equal to 1 by unfolding over t is equal to 1. In this case for t is equal to 1 we will consider this part of the network only. Here in this case the back propagation of error will flow from E1 to through O1 to S1 and then from S1 to S0. So in this back propagation path we can easily calculate the gradient of E1 with respect to V1 and with respect to W01. So calculating the gradient with respect to V1. So this will again, it is possible to understand the entire path or chain rule used in the gradient through net and out functions. So it is out and this is net, and again, so here E1, from E1 we have a backward path to out O1, and from out O1 to net O1, and from net O1 to V1. So we can expand the partial derivation of E1 with respect to V1 as E1 to out O1 and out O1 to net O1 and net O1 to V1. So we will calculate these three values separately and take the product. So our value of E1 is already calculated earlier and it is given here. E1 is equal to half into given O1 minus out O1 whole square. So we'll copy this value for calculation purpose. Here and put it here, take the differentiation with respect to out O1, it will be equal to this value, and just by putting the value we can get this result. Similarly, we can calculate this part out O1 with respect to net O1. Between out O1 and net O1, actually out O1 is a sigmoid of net O1, so we will use this sigmoid relations of differentiation here, and it will be equal to out O1 into 1 minus out O1, and by putting the value we can get this result. The next part is net O1 with respect to dV1, derivation of V1. So we'll expand the net O1. Actually the net O1 value is V1 into out S1. So we'll copy this value V1 into out S1 and take the derivation with respect to V1, and this is the generated output functions. So we will take the product of all three values here and we can get the partial derivation of E1 with respect to V1, which is equal to 0.0435. because the error propagation path of E1 contains V1 and W01. So to calculate the partial derivation of E1 with respect to W01, we will apply the same strategy that we used for the information flow: out, net, out O1, net O1, and then out S1. This is net S1. So the information will flow like that from E1 to out O1, out O1 to net O1, net O1 to out S1, out S1 to net S1, and net S1 to W01. So the information flow will flow in this direction. So we use this in the expense by applying the chain rule. So E1 with respect to out O1 and out O1 with respect to net O1, net O1 with respect to out S1, and out S1 with respect to net S1, and net S1 to W01. So we will take the each of the derivations separately and calculate their value. So our in case E1 is equal to, E1 is already calculated here. So we just copy this value and take the differentiation with respect to out O1, and this is the derivation and this is the result. Similarly, we can calculate this part out O1 with respect to net O1, as there is a sigmoid relations between out O1 and net O1 that we already calculated. So this is our calculation result. Similarly, to calculate the differentiation of net O1 with respect to out S1, we will just use the expansion of net O1. So our net O1 is calculated like V1 into out S1. So we will take this V1 into out S1 and its differentiation with respect to out S1, which will be equal to V1, which is 0.5. Similarly, we can calculate out S1 with respect to net S1, which is again sigmoid type of relation. So expansion will be in this term, in the term of the numerator, and it will be like that. So by putting the value, we can get this result. The last part is taking the partial derivation of net S2 with respect to W01. We will take the expansion of net S1 that we calculated earlier. So our net S1 is U1 X1 W01 out S0. So we'll copy this value here. So we copied this value here and take the differentiation with respect to W01. It will give out S0. So we will put all these values for the calculations, and then after taking the product we will get the value 0.0058. Now the next part is back propagation through time t is equal to 0. So in this case we will cover only this part of the network and discard this part from the calculation path. So from here the backward propagation will follow only this part, as there is no other connections. So we will just use this back propagation through time by applying unfolding at t is equal to 0 to calculate the gradients of E0 with respect to V0, and as discussed earlier it will follow the same path out net. So E0 to out part to net part, and net part to V0. So D0 out O0, out O0 to net O0, net O0 to V0. So as we discussed earlier, error function that we already calculated, we just put the value that we calculated for error functions E0, and this is our error function. We just copy it. We just copy it here and take the differentiation. This will be the differentiation output. Similarly, taking the differentiation of out O0 with respect to net O0. Out O0 is there is a relations between out O0 and net O0, which is sigmoid relation. So again we can expand this derivation as out O0 into 1 minus out O0. You can see the sigmoid relations between out O0 and net O0. So this is out O0 and net O0 sigmoid relations. The next part is to calculate the derivations with the derivation of net O0 with respect to V0. So we will take the expansion of net O0. Our expansion of net O0 is the V0 into out S0. So we will take this value. V0 into out S0 and take the differentiation with respect to V0. We will get this value. Finally, we will take all these values and put it here, and by putting the value we can finally get the gradient of E0 with respect to V0. Now we will use these gradient values. Now we have gradient scores for B2, B1 and B0, W12 and W01. So we will use this gradient score in updating the weight of B2, B1, B0, W12 and W01. So let us start with B2. We have DE2, calculated value DE2 with respect to B2, means derivation of DE2 with respect to B2, which is calculated as 0.0626. So you can see here DE2 with respect to B2. So you can take it 0.60653. So we will take this value. So by multiplying we will get slightly near value than this, and we will use this value. So it will be 0.0653. Actually we made some calculation mistake, so that earlier. So this is the updated, this is the weight for partial derivation of E2 with respect to B2. So updated weight of B2 will be B2 dash. It will be old weight minus learning rate into the partial derivation. So our old weight that we already know, our given weight B2 is already 0.5. So we'll put it here. Learning rate is 0.5. This is the calculated gradient value 0.0653. So it will be near to this value. So we'll use this value to update the neuron V2. Similarly, we can update the weight of V1. We have gradient score DE1 with respect to V1 that we just calculated. Partial derivation of E1 with respect to V1, which is 0.0435. We have old value of V1. We have old value of V1 as 0.5. So 0.5. Learning rate is 0.5 that we already taken, and we put this value here, and by taking the calculation we have 0.4782. So the new weight of V1 is 0.4782. Similarly, we can update the value for V0. V0's old value, which is 0.5. This is the updated weight of V0. This is old weight of V0, which is 0.5, and this is learning rate, similar to the used here. We use it as a 0.5. The partial derivation of E0 with respect to V0. After putting all these values, we will get this value. So this is the new weight of V0. Similarly, we can update the weight of W12 and W01. As W12 comes in a path of backward propagation path for only for output E2, error E2 and output node O2. So we will use only one derivation that we have with respect to W12, which is 0.0077, and updated weight of W12, old weight of W12, 0.5, learning rate, which is again 0.5. We have taken this, and we put it here, and after calculation we will get this value. So this will be the new value of W12. Similarly, we can update the weight of W01. But now it is important to note that at neuron W01 we get the back propagation value which propagated at time t is equal to 2 through E2 and through time t is equal to 1 from E1. So we have two gradients for with respect to W01. First is with respect to E2 and second is with respect to E1. So we will use both values in updating the weight of W01. So the new weight of W01 is equal to old weight minus learning rate. So old weight of W01. So old weight of W01 is given as 0.5. So we put it here. We take the learning rate as 0.5. We take the sum of these two values, and then our calculated new weight for W01 is 0.4967. We use same process multiple times to get the optimal weight for these neurons. For this we will take several different data record. And train the system and calculate the prediction score by forward pass and by using back propagation through time for multiple steps. We can calculate the optimal weight for these neurons. And after the recurrent neural network getting trained, we can put any value. For example, as we discussed earlier, probability value for W1, W2 and W3. Then the predicted score after properly learned recurrent neural network, the predicted score for W1, W2, W3 will clearly indicate that whether W1, W2 and W3 form meaningful sequences or not. Now for further study you can take these references. Hope you have enjoyed this